All right, now we're going to discuss the following problem. So we know that the chromatic number is always bounded from below by the clique number. But one question you might have is how far apart can these two parameters get? In particular, for any pair of integers, positive integers a strictly less than b, is there a graph whose clique number is a and whose chromatic number is b? If there is such a graph, then we can guarantee that there's no way to bound the chromatic number from above with some function of omega. So one example of this would be setting omega equal to 3, or 2 itself. Then we're just asking, are there triangle-free graphs of arbitrarily high chromatic number? So here we're going to discuss the construction due to Misielski. And the idea is that we want to create, given a graph G, we're going to create a new graph called M of G that has the property that has the same clique number, but that its chromatic number increases by exactly 1. And so the advantage of this construction is that if we apply it multiple times to a complete graph, we're going to end up with a graph whose clique number is A, and whose chromatic number is A plus the number of times we did this construction, which is B minus A, which is B. So in other words, by doing this construction over and over, we're guaranteed to create graphs of arbitrarily high chromatic number, but a given fixed clique number. Right, so now we're going to discuss the construction. Our new vertex set is going to consist of two sets of vertices that are clones of the original vertex set. So given our original graph here, let's call these vertices GRAPH. Then what we do is we clone these vertices twice. First V sub G, V sub R, and so on. So that's what I've done. V sub G and U sub G and so on. And then we add a new vertex called W. And then the rule is for every edge in our original graph, like from G to H, we first make a copied edge from VG to VH. And so we do that for each of these 5 edges. So we get an exact copy of our original graph. But now for each of these edges, we also replace one of the V's with a U. So we replace VG with UG, or VH with UH. So I did the picture up here as well. Every edge gets replaced with 3 edges. And so that's the idea here. So I should be creating a bunch more edges here. And then as you can tell, this is going to get a little too hard to draw after a while, but we can sort of manage because we're just doing the same habit over and over, the same policy. And so that should be it. And then finally, for every vertex of type U, we connect it to our new vertex W. And so this is the resulting graph. And so the claim is that this new graph has the same clique number as what we started with, and yet that the chromatic number increases by 1. So before we continue with the proof, I want to redraw the graph, the construction in the case of a 5-cycle, mainly because you can draw the picture slightly differently by putting the V vertices on the outside and then the U vertices slightly in the middle. And then you see for every edge, I've replaced it with 2 edges going from a V vertex to a U vertex. And then finally put the W vertex in the middle and attach it to all the U vertices. And I can explain the rest of the proof using this graph as well. So the first thing we want to show is that the clique number is the same. And so the idea is to consider any clique in the graph. And so the first case is that the clique contains the W vertex. But by definition, it's worth noting that the W vertex only has neighbors in U. And once you have at least 2 neighbors in U, you have something that does not have an edge between them. Because if you hadn't noticed, we set it up so that there are no edges between vertices in U. And so the largest clique you can have involving a vertex W is size 2. which of course was our lower bound anyways. Likewise, the next case you might have to deal with is that you have a clique involving one of the U vertices, for instance, like this one. And as already discussed, it can only have at most one vertex from U, because if you have two vertices in U in your set, then you have two vertices that are not adjacent. And so it has at most one vertex from U, and the other vertices have to be from V. Well, one of the issues is that we had this cloning idea. So this was the clone of this vertex, and the point is if you go back to the V, the other clone, you see that you still have a clique. And so every clique involving a vertex in U can be replaced with a clique involving only vertices of V of the same size. And so the whole point is that for any clique in this graph, you can find another clique just among the V vertices, so the original graph of the same size. And thus that guarantees that the clique number is the same. So here we do the actual formal proof. Let K in the new graph be a clique. If W is in K, then the size of K is at most 2, because you can only have at most one vertex from U, and W is not adjacent to any vertex from V. Similarly, suppose W is not in K. Then, as noted, there's at most one vertex among the U vertices in your set. And if you suppose that that vertex is in some vertex UI is in your clique, then if you replace UI with VI, you also get a clique. And the reason why that is because if UI was adjacent to some VJ, then by definition IJ was in the edge in the original graph, but that means VI and VJ is an edge in your new graph. And so the point is all these vertices in K have to be adjacent to UI, then by this fact they have to be adjacent to VI as well, and therefore this is also a clique of the same size. And thus, given any clique in our new graph, we've seen it's either size 2 or there exists a clique in the original graph of the same size. And since we know that the clique number of G we can assume is at least 2, we're guaranteed that this means that the clique number of M of G is the clique number of the original graph. All right, now the next thing we want to prove is that the chromatic number of the new graph is equal to the chromatic number of the original graph plus 1. So first we want to show inequality one direction. And so suppose we have coloring of the original graph with the minimum number of colors. So in this case it has to be 3 because the graph on the outside is an odd cycle. Then the strategy is to color the VI vertices with the same colors, and then to color the UI vertices with the same colors. And then the claim is that you can see that you still get a proper coloring so far, because anytime a UI was adjacent to a VI, VJ, then VI was adjacent to VJ and they had distinct colors. So the proper coloring property is preserved, but more importantly, you see that the last vertex W has to be colored with a new color. So this shows us an upper bound, but you also have to prove that there's no way to get a better coloring. All right, so now we are in the place where we want to show that the chromatic number is increased by 1. First, I want to give the upper bound. Suppose I have a coloring of G with K colors. Then I'm going to create a new coloring of M of G using K plus 1 colors as follows. I'm going to use the original coloring if I have a vertex of type U or V by just giving it its original color. So I'm taking each vertex and I'm splitting it into 2 and keeping their colors. Then finally I'm going to assign my brand new color K plus 1 to the W vertex. And so this turns out this F prime is a proper coloring. Why? Because anytime you have an edge involving a vertex in U, it must be adjacent to W, which has a distinct color, so it's a proper coloring, or it's adjacent to a vertex VJ, And then if ui is adjacent to vj, then vi is also adjacent to vj, and I is adjacent to j. And it's worth noting these had to have gotten distinct colors before. And so now they have to have distinct colors here too. And so you do see that you have a proper coloring. So that gives you the upper bound. Thus, the chromatic number of m of g is always at most the chromatic number of g plus 1. Of course, you might wonder if it's possible that they end up having the same chromatic number. And so that's going to be the second half, and we're going to proceed by contradiction. Or more accurately, we're going to take a possible candidate coloring using chi of g colors and show that there's a monochromatic edge, and so that it's not proper. And thus that will rule out the possibility that these two graphs have the same chromatic number. And so let's take such a function. Notice that it involves using chi of g colors. And so I'm going to create a smaller color set by throwing away the color used on vertex W. And I'm going to call the remaining color set X. I'm going to create a new possible potential coloring of G as follows. When I have a vertex that originally got the same color as FW, so f of vi and f of w get the same color, like in this situation, then I'm actually going to use the color given to ui instead. So f prime of I is going to be f of ui in this situation. Otherwise, I'm going to stick with the color of f of vi. So if vi had a different color to begin with, I would pick that instead. So the point is that since this color set is smaller than our chromatic number, we know there must be an edge whose endpoints got the same color in f with respect to f prime. So there has to be an ij with f prime of I equal to f prime of j. Well, then we're going to go back to our original graph. So we look at vi and vj, and we ask ourselves, okay, did these two vertices get colors different from w with respect to f? If so, then by how we did our coloring, f prime of I is equal to f of vi, and f prime of j is equal to f of vj, and congratulations, we have a monochromatic edge involving vi, vj, and thus we have something that is not a proper coloring. So our original function was not a proper coloring of m of g. Case 2, f of vi is equal to f of w, but we have f of w is not equal to f of vj. Then what happens in this case is f prime of I is equal to f of ui, f prime of j is equal to f of vj, and congratulations, we have a monochromatic edge involving one of the u vertices. So f is still not a coloring. Then the third case is that f of vi is not equal to f of w, but f of vj is not equal to f of w. This is similar to the previous case. Instead, you get the situation that you're looking at f of vi versus f of uj instead. So then you start to see case 4, f of vi is equal to f of w, and f of w is equal to f of vj. If you go through this argument, you would end up concluding that f of ui is equal to f of uj, but since ui and uj are not adjacent, that doesn't seem to be a contradiction. But it turns out you have a simpler argument. You're already declaring that these two vertices have the same color. So they already have the same color, and they're already adjacent. And so you found a monochromatic edge. And thus what we see is that using a potential coloring of mg, using fewer colors, we found a monochromatic edge in G, and then we converted it into monochromatic edge in M of G. And that's our contradiction argument to show us that the chromatic number has to increase by exactly 1.